Sorry. So, hi everyone, welcome to today's session on linear algebra through geometry. So let's wait for a few more minutes so that others can join. Hi, am I audible? Am I audible?
Yes, sir. Good evening, sir.
Good evening. So let's wait for a few more minutes so that others can join and we'll start them.
Okay, sir. Yeah.
So, hi everyone, is my screen visible?
Yes, sir. Yeah, it is.
Sure. So, we'll start today's session and hmm, right. Okay, fine. So, let's begin. So, so this is the last week for this course, right? So, so let's finish whatever is remaining, right? So yes, in this week you all saw about one of the most fundamental matrix factorization methods, the singular value decomposition. So the most important property of a singular value decomposition is it exists for any kind of matrices. So it basically exists for any matrix, right? For any M cross N matrix, M can be greater than N, M can be less than N, M can be equals to N. Anything. It exists for any kind of matrix, right? And again, as usual, as we saw with matrix factorization methods, various matrix factorization methods, we know that SVD can be useful for solving systems of equation, as there are many applications of as singular value decomposition. And the most important use case is for defining some useful properties in a system if the system can be written using a matrix, right? So we will see what I'm meaning by these statements, right? Now, SVD says we can write a matrix, any M cross N matrix, right? Any M cross N matrix as a linear combination of N rank, K rank 1. Sorry, either here we have taken the number R, right? So we can write any matrix as R uh, rank 1 matrix, linear combination of R rank 1 matrices, right? And those rank 1 matrices are given by so the coefficients, coefficients for the linear combination are given as the singular values, basically sigma I that you can see here, and the matrices are given as ui dot into vi transpose. And we all know that if you have a matrix U, a vector U, and you have a vector V, then UV transpose forms a matrix which is having rank 1, right? This we know, right? This is very well known to everyone, right? So basically, SVD theorem says that you can write any matrix A of dimension m cross n as a linear combination of R rank 1 matrices, where the number R is essentially the rank of matrix A, right? Now, uh, basically, when you try to write something like this, you can always write this in matrix form so it's a linear combination. So you can always write a linear operation. So you can always write it as a in matrix form. So it can always be written as U sigma V transpose, where the matrix U, okay, so the, let me write here. So the matrix U contains the column vectors U1, U2, and so on. As you saw here, the UI vectors, right? Similarly, sorry, right. So similarly, matrix V contains the vectors V1, V2, and so on. And when you write the system as A equals to, when you write this product, matrix vector product, U sigma V transpose, you will observe that this quantity will be equals to this thing that we are writing here, right? The linear combination that we are using here, right? And most importantly, this sigma, what is this sigma matrix? Sigma is a diagonal matrix, right? Sigma will be a M cross N diagonal matrix containing the singular values, some values that are essentially known as the singular values, right? So other entries will be 0. It need not be square. It can be rectangle. So sigma always has the dimension of the original matrix itself, right? So these are a few basic definitions for singular value decomposition. Do you have any doubts in this? Anyone?
So, sir.
Right. So the question is, right. So we have defined something. We don't know how it came and what is, but we have defined something right now. Yeah, Satinder, you have a doubt. Let me just. Yeah, what is the doubt?
Uh, Sir, like I want to know, like when we are calculating no U and V.
Hmm.
So, like we are calculating. I think A transpose A.
Yeah,
Eigenvector of
I'm
A.
getting to that. I'm getting to that. Yeah.
Okay, okay.
Right. Right. So this is a definition of singular value decomposition. Why we get this? What are the properties of singular value decompositions that we haven't seen right now, right? Okay, fine.
Like one more thing, like is it same as the projection one what we did in the that part? No, ki it actually it represents the projection of the B matrix, like no U transpose, like we do no for the projection matrix. So it is somewhat like that
Okay.
also.
Basically, here you are not, you are essentially projecting in the space spanned by the matrix UI into VI transpose. It's not U transpose, right?
Okay, okay. So somewhat that concept it has been, I think, taken from that only, no, like projection matrix, like only, like what I am getting little bit. Ki V actually it is rotating, it is making orthogonal means rotation of the axis nine basis V, and sigma I think scaling is there, and U is again what we have done the rotation, that again it will return it back to the original place. I think somewhat it is that concept.
Yeah, fine. So we will see what it says, right? You are right. So yeah. So this is about a definition of a singular value decomposition. Now the thing is, how can we reach here? What are the properties of these values and what do they actually represent, right? So let's go back to one concept that we already saw in the previous lecture, previous session. That was eigenvalue decomposition. I hope every one of you remember this, right? Fine. So what was singular? What was eigenvalue decomposition? Basically, you can write any matrix. You can write a matrix. So for any square matrix, you have a space where you can define a space where if you choose a vector from that space, if you choose a vector from that space, right? Where such that for a given matrix, for a given space of some, for a given matrix A, that such that AX will be equals to lambda times X. Basically, if you multiply that vector, transform that vector after by using multiplication with uh, this. Just 1 minute, guys. Yeah. Yeah. Sorry for the interruption, right? Yeah. So what we were saying that we have something known as eigenvalue decomposition that we already know. That comes from the idea of eigenvectors and eigenvalues, which says that for any square matrix, you can define a space S such that you will find a space S such that if you take a vector from that space, then you will observe that if you transform that vector by using matrix multiplication with the matrix A, you will observe that that vector will only be scaled by some amount, and that amount is known as the eigenvalue, right? So this is the eigenvalue, and any such x is known as any such x is an eigenvector. So we all know this and we remember this concept, right? So let's only stick to this concept, right? And let's try to see what it means geometrically, and then we will go to the geometric definition of singular value decomposition, right? Fine. So we all know this, and we don't know to do. We don't need to do anything extra here, right? Let me make some space. Okay, so let me all of this. Yeah. So now, yeah. Now let's see what it means geometrically, and then we can build from there. So let's say we have this vector space, right? The usual Cartesian plane, XY plane. Let's choose this basic Cartesian plane, and let's say I'm defining a vector in this space, right? So so I want to represent a point in this space. So let's choose this point, the point 1 comma 1, and this point can be represented using the vector that goes from the origin to this point, right? This vector, right? Now what eigenvalue decomposition says, if the vector 1 comma 1 lies in the is an eigenvector of a matrix A, vector of a matrix A, then you will see that A into 1 comma 1 will be some lambda times 1 comma 1. This means this vector will only be scaled by some amount in the same direction, right? It won't get translated or rotated, right? So it will get scaled by some amount, lambda into 1 comma 1, right? So this is what A into X looks like. This is what geometrically eigenvalue decomposition says. Fine. Now, the thing is, right now, let's say if 1 comma 1 was not an eigenvector, then what you could have observed, you could have observed the basic operations, the operations such as scaling, linear operations, basically scaling and rotation of the vector, right? Let's say if I have chosen this vector, I would have chosen this vector would have mapped to some other vector, right? Which would have been rotated by some amount and scaled by some amount s, right? So if it was not an eigenvector, but since it's an eigenvector, it's only being scaled, right? So it is only being scaled and no rotation will be observed. Fine. So this was all about geometric meaning of uh, eigenvectors, right? Now let's say we have a general M cross N matrix. A is a general M cross N matrix where M is M and N can be anything, right? Can be any positive integer, right? Right? Or zero also, right? Then, uh, uh, then what I want to you guys to see is, let's say I write A as I define a new matrix. I define a new matrix A transpose A, right? So now anyone, can you tell me what is the dimensionality of this new matrix? This will be n cross n, right?
Yes. Yeah.
Fine. Now you have this matrix, right? Now I want to say that I want to observe, I want to find the eigenvalue of this matrix, right? Well, I want to find the eigenvector of this matrix, right? So let's try to do this. So I was saying A x equals to lambda x, and then A transpose will be X transpose A transpose. Hmm. Hmm. Right. So now I know this property. Now let's multiply A transpose with it. So A transpose AX equals to lambda, right? Lambda into A transpose X, right? Can we say something from here? No, not right. Huh. So yeah, we can't say something directly here, but we know one useful property. Now, can you prove that for a given matrix A transpose A will be square given a real matrix, right? Real A matrix, real. Then A transpose A would be a square, real, and symmetric matrix. Can we prove this, everyone?
Yes, sir.
Fine.
Real and
There
Yes,
are
sir.
no doubts
yeah.
in this, right?
No, no, yeah. Okay.
Fine. And now we know very useful property of a real symmetric matrix, right? Real square symmetric matrix. Basically, symmetric matrix means it's a square, right? So, what is the useful property? It is orthogonally diagonalizable, right? Diagonalizable, which means you can write A transpose A as what P some lambda into P transpose, right? Why I'm writing P transpose instead of P inverse? P inverse equals to P transpose because P is an orthogonal matrix, and we all know that why P will be orthogonal because the or original matrix is a mm, what we call it real symmetric matrix, right? Now, yeah, this is good, right? So, right. So this was this we all know that its eigenvalues will always exist. So this means that if you have a matrix of dimensionality m cross n, right? If you have a m cross n matrix, then its eigenvalues will always exist, right? So and it's always basically always exist means sorry, it means that it will have real eigenvalues and it will be diagonalizable basically. You can write it like this, right? Now the another interesting thing that we want to figure it out. So one thing, one doubt might come. Let's say what happens if m is less than n, right? In that case, you can choose the matrix A transpose, and you will observe this similar properties, right? Yeah. So now you have got this, right? From here, can we build upon the eigenvalue decomposition, right? Now, what I said, what we saw that uh, how to say this? A transpose A is AX equals to A is not S one, right? So now we all know that we have something we can build this, right? And now what we want to see is what this eigenvalue of this matrix looks like, right? So I am saying A transpose AX equals to lambda X. So what this lambda looks like, right? Hmm. Right. So now let's say I'm saying this decomposition exists, right? Use sigma V transpose. So then what A transpose A looks like, it becomes, we all know this, how to get to this. UV sigma transpose sigma, right? Sorry, sigma transpose into U transpose U sigma V transpose, right? We can always write this if we assume that such decomposition exists. And given that U and V are orthogonal, this is orthonormal, and this is already in the definition of SVD, then you can see that this becomes V sigma transpose sigma into V transpose, right? Now, can you observe some pattern from here, a matching pattern between these two? It says that V sigma transpose sigma V transpose is equals to P lambda P transpose. Now, if I am able to write a matrix, let's say A cross A transpose A as some matrix, then some other diagonal matrix, and then its inverse, then we can say that this is an eigenvalue decomposition, right? So from here, you can observe that this is the similar, these two equations are similar. This means that sigma squared will be equals to lambda, right? Now, this gives you the definition of singular value decomposition, right? So this is how you can compute the singular value decomposition of a matrix. Now from here you can always compute the singular values. Now sigma transpose sigma, you all know it's a diagonal matrix. So product of two diagonal matrix is a diagonal matrix, and if both are same, it becomes sigma squared. So this means each of the diagonal entries will equals to angular eigenvalue, and then you can take the singular value as a square root of that eigenvalue, and you will get the singular value, right? Now, one thing to know here is that this lambda, this eigenvalue of A transpose A, will always be positive. That then only you will be able to take the square root. So, and you can always prove that this will always be positive. And from here you will, and you always take the positive square root of this square positive value. And this gives you the definition of singular value decomposition. Is this clear, everyone?
Yes, sir.
Right? Now again, you don't need to do anything extra. Just think of what it means. It means that you can write this matrix A transpose A as V, some eigenvalue matrix, and then V transpose. Now, what it is doing to a matrix, to a vector, right? A transpose AX. What it is doing to a vector, right? X, right? So V transpose. Again, now we are again going looking at the geometry of the problem, what it's doing, of the decomposition, what it's doing, right? So let me bring it some good place here, right? Now let's go back here. Now, not I have we have established that A transpose A can be written as V sigma squared and V transpose, where V is some orthonormal matrix. Then let's say I am just doing this thing, A transpose AX, right? So what will it become? It will become V sigma squared V transpose X, right? Now what is so let's say you have a vector X, then what is V transpose X? What it will do? It's an orthonormal matrix. So what it will do? It will simply rotate the vector, right? So let's say you had this vector. So let me remove this picture here and then redo this thing for a singular value decomposition, right? So you start with a vector like this. So what V transpose X does, so V is a orthonormal matrix. So what it does, it can only rotate it, right? So it will rotate this vector somewhere, right? Now what you are doing, you are multiplying this vector with some a diagonal matrix, which is essentially containing positive diagonal elements. So what it will do, it will scale this vector by some amount. So let's say it has scaled it to become this much big, right? Now what again, v into this scaled vector, let's call this um, some x dash. So what does v x dash will do? So since V is the inverse of a V, right? V is essentially V transpose inverse. So it will do the inverse operation of what V transpose was doing. So V transpose rotated in the anti-clockwise by some angle theta. So V will essentially rotate it by angle theta in the clockwise direction, right? Do the opposite. So it will simply rotate the vector like this and it will come here, right? So essentially, in some way, you are only doing a scaling operation if you multiply by A transpose A matrix, right? Everyone, do you get this?
So, like, if the question will be asked, like SVD is it's just do scaling or just rotation and then scaling. So, what should I write? We write in the option then.
No, what SVD does is nothing. SVD just is a theorem that
Uh,
says that you can write a matrix as a product
yeah.
of an orthonormal matrix, then a diagonal matrix, and another orthonormal matrix. That's
So,
it.
when we are applying this option, no, because there was a question I think in the assignment, this
Mhm.
type of question. First it rotates and then it scales, or just it is scaling, something like that question was there. So
Yeah,
in
right.
that type.
Basically, it says when you are multiplying a matrix with a vector, then can you
Mhm.
say what it is, what operation is being happening? using the
Mhm.
singular value decomposition. I guess this might be a good question. Like, what does this operations mean? So V transpose
Yeah.
X is basically rotating the vector, then sigma is scaling the vector, rotated vector, and U is again rotating the vector into some other space, right?
Mhm. So overall action is just scaling, nothing else.
No, basically rotation and scaling, both things are happening, right?
No, no,
And
like
most importantly, this
first
sigma is
rot-
not a square matrix, right? This is not a square matrix, it's a rectangular matrix.
Mhm.
So you are completely
Actually,
transforming the basis from input space to output space.
so maybe dimension has been added or dimension has been removed. Maybe it is also there, no? Higher dimension to
Right.
lower dimension, the things has been scaled.
So think of it like this, use sigma V transpose, right? So now you have a matrix A that had some input space and some output space, right? So it was taking inputs from the Rn dimension and transforming them to Rm dimensional vectors, right? Now what we are saying is, so now V spans the which space? V spans the input space, right? So V spans Rn space. V does its operation on the vectors in Rn space. Sigma is essentially again transforming vectors from Rn to Rm, right? Now U is transforming vectors in Rm, right? So entire change of space is happening. This is how your input is. So here we only saw the abstract view that matrix takes a vector from Rn and then transforms into Rm space. But in what is going on inside is, first a vector V operates in the input space, rotates the vector. Then there a scaling matrix scales the vector and all as well as transform it from the Rn space to Rm space. And then finally another rotation matrix U, orthogonal matrix U, basically rotates the vector again in the output space, which is Rm space. This is what is happening in as a whole when you do matrix vector product, right? And you can always see this using this image also, right? So you have a column space of A, column space of A transpose, null space of A here, null space of A transpose, right? So basically, what it does is it takes input, which is basically in somewhere here, then it transform it to column space of A, right? But it is not done directly, it does something in between, right? Is this clear? So it's not straightforward. When you are transforming vectors from one space to another space, you are not simply scaling and rotating them.
Sir, I have one doubt. Uh,
Yeah,
can you come to a blank page?
yeah,
So yeah. So for eigenvalues, uh, uh,
yeah,
so for eigenvalues, where we were considering only square matrices. So let's say A is a n by n square matrix.
yeah,
The operation is happening from Rn to Rn, right?
yeah.
And when I'm looking at eigenvalues, so
Mm,
my consideration is about what are the vectors that I can
mm,
multiply with this A matrix so that they
mm,
remain in its path only. Maybe some kind of scaling will happen only,
yeah.
stretching or
Mm,
compression. Yeah.
mm,
So when but when I'm considering the general case, that is when
mm,
I'm considering A m by n case,
mm.
right? So now, what kind of vectors actually we are trying to find? So basically, using SVD, we are trying to see some kind of operation. Earlier, we were
Right.
trying to see
First thing, we can't say this, right? We can never do
right,
this,
right,
right?
because
This
Rn
is
to
wrong,
Rm is happening, right?
right? Then what SVD is trying to do, right? So what SVD is trying to do is, it's trying to factorize this matrix as a product of three matrices. The first one is an orthonormal matrix, then a diagonal matrix, and another orthogonal matrix, orthonormal matrix, right?
Right.
So
Yeah.
this is what SVD tries to do. Actually does. This is what SVD decomposition theorem says. This is what factorization essentially does. And the thing is, you can prove that this exists for all kind of matrices, depending and independent of the size of m cross n. Right? You will be able to write any matrix in this form. Now, what it is geometrically trying to do? It is not doing something that eigenvalue decomposition was doing. What it will do is, let's do this. So let's say this is your matrix input space and this is the output space, right? So it was taking vectors in Rn and transforming into vectors in Rm. right? Let's assume
Right.
this kind of setup. Now what it is doing is it takes so now what you do, you simply say u sigma v transpose into some vector x, where x belongs to Rn, right? So let's say I have a vector in Rn space, right? Then you will what it will do is it will it becomes like av equals to u sigma, right? So this is a vector in Rn space. Now what you're doing, you are rotating it using some orthonormal matrix V here, V transpose basically, right? In the input space itself, right? So it's something that it's a matrix multiplication that transforms the vector into its own space, right? So it will simply rotate this vector into some new kind of vector like this, right? Now what this
Right.
sigma matrix is doing, this is essentially transforming this vector, mapping this vector to a vector in the output space, right? It will map this vector to a vector in some output space. Now, finally, what will happen? You will multiply it with some matrix U, which is again an orthonormal, so basically doing a rotation, but in the output space, right? So it will rotate it by some amount in the output space, right? So, and then you will get the final vector, right? Then you will get the final transform vector. So this is what eigenvalue, SVD theorem is saying. That's it, right? Now,
Okay.
now what I have done here is you can always see this as just simple example. Now, let's say this is something that we have expanded upon the simple matrix vector product that we used to do earlier, right? So let's say this was the Rn space, the input space, and this was Rm space, and then you had a vector in Rn space. Then what you were doing when you multiply with a matrix A, you simply transform it into some vector in the Rm space, right? You remember this, everyone?
Right. Right.
So basically what I have done here is just simply given some more details, added some more details that shows how everything is going on inside the picture, right? That's it. Now this vector is the input vector. This is same as the input vector. Now this output vector is same as the output vector that we saw here. It's just that we have given additional details. Like first it was rotated in the input space still, then transformed to the output space, and then finally rotated in the output space. That's it. I have added more
Right.
details. That's it.
So let's consider small
Hmm.
v1 is an
Hmm.
eigenvector of A transpose A, whereas
Okay.
small v1 is an element of capital V.
Yeah.
Right. Let's say consider small v1 is the first column of capital V.
Yeah.
So small v1 is an eigenvector of A transpose A, right?
Right.
So suppose I'm multiplying small v1 with capital A matrix in its SVD form.
Right.
So it will be
Let me
U
see.
sigma.
M cross n. This is n cross n, and this will be n cross 1. Right. Yeah. Then.
Right, yeah. So can you write A v1 equal to U sigma V transpose into v1? It will be helpful for me to say then. A equal to
Right. Yeah.
yeah,
Yeah. What you're saying? AV1 equals to.
yeah, right. U sigma V transpose in its uh, SVD form. I was trying to represent A in its SVD form and then
Right.
multiply
Right.
it by
Right. Right.
v1. Yeah,
U sigma V transpose into small v1. Right. This
right,
you want to see what it
right,
looks
right.
like, right?
Yeah.
So
So
basically, v1 will be essentially the first column vector of V matrix V here itself that we already saw, right?
right, yeah.
We already saw that v1 is the first vector of the V transpose, right?
Hmm.
Hmm. There's nothing wrong with that, right? So now what you are doing, you are simply doing V1 transpose V transpose V1. So what this will look like?
It will be a n. It will be a yeah. It will be n by
Hmm.
one matrix only. It will be essentially only v1, right?
E- No, it will be V1 dot V1. That will be one first diagonal, and all
Huh.
other entries will be zero, right?
Okay, right, right, yeah.
So this will become something like this, and then U sigma something like this, right? And then sigma into this will essentially be U into sigma 1 into this, right?
only sigma 1 will be there because
Yeah,
rest of
right,
the
right.
diagonal elements will be 0.
Yeah, and this will become sigma 1 u1. So basically
Right.
what we are saying is a v1 equals to sigma 1 u1. That's it.
Right. So I have essentially the doubt I have is something
Hmm.
related to this. So for
Hmm.
eigenvalues, the
Hmm.
largest eigenvalue, it was telling me something. So the largest eigenvalue was, suppose lambda 1 or lambda
Hmm.
max is the largest eigenvalue of a square matrix. Let's say
Hmm.
a n by n, or
Hmm.
let's give it another name, b n by n. So
Hmm.
B matrix has this largest eigenvalue,
Hmm.
lambda max, and
Hmm.
it tells me that okay, so if I multiply
Hmm.
B matrix with any vector, at
Hmm.
most it can stretch that vector
Hmm.
by lambda proportion. So
Right.
here, since it is taking to the completely new region Rn to Rm,
Hmm.
A is not remaining the vector to Rn itself,
Hmm.
right? So here the singular value is telling me what stretching amount, like it is stretching it definitely. So here the largest singular value tells me exactly what. So I have confusion there actually.
Right. So basically, first of all, we should not directly compare eigenvalues and singular values, right? Values are not exactly equals to singular values, right?
But yeah,
And
kind of
again, what
generalization
this
of that.
largest singular value is saying, like that's the question, right?
Right.
So, so think of it like this. So when you multiply a matrix X with a vector X, what it can do? It can scale,
Right.
rotate, right? Or do any combination, right? Any
Right.
combination of these or reflect also. Let's ignore that reflection also.
For a square matrix, right? And for a different
No,
matrix, it
for
will
any
take it
matrix,
completely.
for any matrix.
Uh, uh, but if it is a rectangular matrix and m
Hmm.
is greater than n, let's say 7 by 3,
Hmm.
let's say is a 7 by 3 matrix.
Hmm.
So then we are moving from R3 to R7. Then
Right,
only
right. So
scaling and
what
rotation is
it's
not
doing
happening.
is, what it's doing is again, what it's doing is first it is scale doing some rotation in its own space, R3. Then it is transforming it into R7 and then scaling in R7 and then finally doing another rotation in R7.
Right. So
Right?
that's what I was saying. Not only scaling and rotation is happening, transformation component should also be there for a
Yeah,
rectangular matrix.
yeah. So what is the doubt here?
Okay. So number one, I was trying to interpret maximum singular values definition. And
Huh.
number two, am I wrong if I say that singular values are generalizations of eigenvalues? Or if I try to think of it like this?
No, 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 no. That's not. Because singular values exist for all kind of matrices and then eigenvalues don't, and eigenvalues can be negative, whereas singular values can't. So if you're
Correct.
talking about
So I was,
generalization, then the eigenvalues should be fit in the definition of singular values, right?
but isn't eigenvalue is what motivating us towards singular value? Or like
I
eigenvalue
mean,
is
they are a motivating point and they are a way, one way of computing. They are the way of, this is the only way this is the way that you have seen how to compute singular values. But this does not mean that singular values are a generalization of eigenvalues.
okay. Okay.
This is something that we came across, like that we were able to prove that if you want the singular values, you can proceed from by computing the eigenvalues of matrix A transpose A.
Okay.
Fine.
Right.
Second thing, what is the geometric significance of this largest or what any singular value, right? So
Right.
again, we go back to the same thing. Let's say we had a input space and our output space. This was Rn, this was Rm. Now, what does singular value signify here? If you choose any vector in the Rn space, right? You choose any vector in the Rn space, you know that it will be transformed into some vector in the Rm space, right? It will be transformed into some vector in the Rm space. Now, right, this is something that we agree on, right? It's a
Yeah.
linear transformation. So it will be if you multiply it with the matrix A, you will get some vector in the Rm space, right?
Right. Yeah.
Right. Now let's say if I choose the space of all unit vectors in the input space, I am fixating my space to be the space of all unit vectors into the input space, right? So let's take all the vectors in this unit circle in the input space, right? Now, can we choose this, right? We can choose this always.
Right.
Now, when you are multiplying this vector with the matrix A, you will observe that uh, this vector will form another vector in the output space, which will again which will again have some magnitude, which will not equals to 1, right? This we agree on, right? If you have a matrix A and have a unit vector x cap, it's not necessarily that the magnitude of y will be 1, right?
Right.
Not necessary
Only if the
always, right?
singular value is one itself.
Yeah, right? Not necessary, right?
Right.
This means we can have this means we can have arbitrarily scaled vectors in the output space that need not to have norm 1. The second thing is, you will observe that if you choose this unit vector in the space of all the input vectors as the vector corresponding to the first singular value, right? So I will say that AV equals to U sigma, right? Now, if you choose the first right singular vector, right? AV is essentially what it's doing. V contains all the singular vectors, V1 up to Vn, whatever, right? Now,
Right.
AV is basically the matrix AV looks like AV1, AV2, and so on. And this becomes sigma 1 U1, sigma 2 U2, and so on, right?
Mm.
Now note that this all these vectors v1 vn up to vn and u1 up to un are unit vectors, right? Unit vectors. Now what does this sigma 1 u1 signify? Now this is the vector that we are observing here, right? This is the vector sigma 1 u1, right? And this input was our v1, right? Everyone? So Rohan, is this clear?
Yes, sir. Yeah.
Now your question is what this sigma 1 u1 signify? What specific property does it have, right?
Right.
First of all, it has some scaling factor sigma 1 which is non-zero, no, non-negative, right? Sigma 1 has to be positive, right? Second thing, something that you will see in future if you go more in depth about SVD is that this will be the largest scaling that you will observe in the output space.
Okay.
So let's say I choose multiple vectors like this, V2, V3, V4, something like this, and I transform them all, right?
Mhm.
You will observe that none of them, the output of all these matrix vector product, none of them will be having will be having length greater than the sigma 1 u1 vector. So their norms will be less than sigma 1.
Okay.
I not equals to 1 will be less than sigma 1. So this is the main crux of singular value this is one of the useful properties of singular value decomposition.
It should be AVI, no? AVI's norm should be less than sigma 1. Is that what you're trying to mean? Because norm of
No,
VI would be 1 for everything, if you're considering VIs. They all are
oh,
orthonormal, right?
sorry. This will be sorry, sigma IUI, right?
Okay.
Sigma IUI, yeah, or
Right. So,
AVI, obviously.
okay.
So it will be sigma IUI, I not equals to 1,
Okay. Right.
right? So
Yes, sir.
this
Yeah.
what information? Let's say if you know this now you know that sigma 1 is the maximum scaling in the output space, maximum scaled vector in the output space. Then what you know from here? You know that given any vector in any direction, the maximum you can scale that vector, the maximum output, maximum norm vector that you can get in the output space is the vector that aligns with the first left singular vector, right?
Right. Yeah.
Right. Now, how to prove this, how to do this, this is not in the scope of for this course, but you can always go back and see how to prove this.
Okay.
What
Okay. So, yeah.
happens is
Got an idea.
this left singular vector span the input space, and the right singular vector span the output space. Now you have a set of basis vectors for a space, then you can always define the maximum scaling, which direction is getting the maximum scaling using singular value decomposition. Right?
Okay. Right.
Any other doubts?
No, sir. Okay. Yeah.
So this was it about singular value decomposition, right? Now, a few more concepts that were taught in this week was how to use these linear algebra properties that we have seen.
Yeah. Uh,
Yeah.
excuse me, sir. Like just I'm asking, when we are calculating V transpose,
Hmm.
so that will be like A transpose A we have calculated.
Hmm.
From there, we are finding its eigenvector, eigenvalues.
Hmm.
So by substituting again with eigenvalues in the A transpose A determinant, like A transpose A minus lambda I, whatever we get,
Hmm.
from there
Right.
we will find the eigenvalues.
Right.
So what the eigenvalues are getting,
Hmm.
uh, that is your V. No,
Wait
are
a
you
minute.
getting?
A transpose A minus lambda I. Right. Huh. Right.
Uh-huh. So now we are finding the eigenvectors corresponding to this.
Right. That is basically the null space of A transpose A minus lambda I. Right.
So what we are getting, that is V.
Hmm.
Then we are taking the transpose on V transpose. So
Yeah.
that is what we are getting. That is eigenvectors corresponding to A transpose A.
Hmm. Yeah. Right.
So my question is like lambda is to not the actual eigen vector, no, eigen values. It is to actually sigma, no, that is
No. Again, lambda is something else.
lambda is the product of eigen values, no, product of two eigenvalues. Two eigenvalues has
No.
been decomposed,
Lambda
no,
is
now
basically
that
eigenvalue of A transpose A. That's it.
okay. So that
Right.
A transpose A lambda now we are calling it as sigma square, no.
Yeah, lambda is essentially sigma squared. You are right.
So when we are applying A transpose A minus, we have to write no, because what we are getting now, we are getting sigma square actually. So we don't have to put lambda I, no, A transpose A minus lambda I, we don't have to write. We have to write, I think, A transpose A minus sigma square I. From there we get, I think, we
Ah,
know.
you can always write that also. You are simply changing the variable from lambda to sigma squared.
Okay. And to get like for
But
you
basically,
to
this will
calculate.
be a way to solve for sigma values, but this is
Mhm.
not the exact definition of SVD, right? Essentially,
No,
you try to find the eigenvalue of this matrix A transpose A, and
for,
in during the process, you will find that the eigenvalues will be equals to square root of the signal value of that matrix.
Mhm. Actually,
Right.
my target target is to calculate V transpose. So to calculate the V transpose, we have to do this all calculation. Then only V transpose will come. I think so.
Ah, yeah,
For
right.
thing.
You're right.
And to get U, so should we use A AVI by sigma, or should I use A into A transpose
So this is very
eigenvectors?
simple. Let's say you got A equals to U sigma V transpose, right?
Now we have calculated V transpose.
You have calculated V transpose. It is known. You know
Mhm.
sigma values, so this is also known, right?
Mhm.
Right. So now you can see that now you can invert this matrix, right? You can always find the inverse of V transpose. That will be V transpose inverse would be V, right?
Mhm.
So you can bring it here. So it will become AV equals to U sigma, right?
Mhm.
Now again, U sigma will become what it will become? It will become sigma 1
AV by
U1,
sigma.
sigma 2 U2, right?
Hmm. So U
Right.
comes out to be AV by sigma.
Ha.
But now the problem is like now the dimension of U will be more than dimension of V. So we have to use Graham-Smith method to orthonormalize again for projection one, no? Because U
So
dimension will be more, no, than this. Because if you are applying this one, so its dimension will be less.
No, both has column number of columns same, no? Both has number of columns as
Like U is M cross M, V
Yeah,
is
right.
V is N cross N. So I think there will be dimension. Means still we have to find more U vectors. No, it is
no,
needed.
you have
So I
exactly
think Graham
same
Smith.
number of, right? Because both side you have n number of columns, so that gives you the exact equation which you state that sigma 1 ui is equal to v1. So just dividing by sigma 1, you can get
No, N
right, right.
cross like
You can always
Both
do
had the
this,
same
right?
number of
Sigma
columns.
2 ut equals to AV2 and so on. Sigma n un
Right, right.
equals to AVN, right? Can you do this always?
yes, sir.
So what is the problem in this?
This I thought ki U dimension will be more. No, like suppose the matrix is suppose 5 cross 3.
Hmm.
So dimension of U will be 5 cross 5. No.
So let's do this. What is AV matrix? How will it look like?
Be like 5 cross 3 into 3 cross 3. No.
So this will be 5 cross 3, right?
Mm.
And on the right hand side, I am writing U into sigma. Now this is 5 cross 5 into 3 cross 3, 5 cross 3. So it will again 5 cross 3, right? This product will be 5 cross 3, right?
Okay.
Now from here, can you figure out the singular values of, can you find, now again, when you do this, the most beautiful thing happens here is you will observe that you will see that this right hand side, you will observe this kind of pattern. Sigma I into ui, where sigma I will be a scalar and you know that value. So you can do the scalar division, right?
Okay.
So from here you can figure out, right?
Mhm.
Is this clear?
Like thinking ki you to decompose U into the orthonormal like orthogonal no eigenvectors. What the eigenvectors will we are getting in U, that will be also orthogonal. No?
They will be
So it will be 5
orthonormal.
cross 5. Ortho
Yeah,
means it will be orthonormal.
yeah, it will be 5 by 5. Yes.
So 5 by 5. So what I'm observing ki we are getting here U3
U will be
like
3 by 3,
sigma.
right? V will be 3 by 3 and U will be 5 by 5, right?
So when we are using the equation, no, so the problem is like what I am able to see here. I think by considering the equation, we get only U1, U2, and U3 only. No, by this equation, we are not going to get U4 and U5.
Okay, so that's what you're saying, right? So,
Mhm. So I think
um,
Graham Smith method we have to apply for the projection
you
one.
can apply, yeah, that always works, right? AV1,
Mhm.
V2, AV3, right? So then what will be U4 and U5? You can apply Grant's fit to get AV4 and AV5. That will work, yeah.
This only I was
Uh,
asking.
sir, yeah. So what was the thing you said at last? I didn't get that part. Uh, about applying Gram Smith.
So basically what happens is you have V1 equals to sigma 1 U1, A V2 equals
Right.
to sigma 2 U2, A3 V equals to sigma 3 U3, right? Now
Right.
you
Yeah.
know these three left singular vectors V1, V2 and V3. How you know? You did some sort of you did a eigenvalue decomposition of V transpose and A transpose A matrix, right? From here you get sigma 1, sigma 2, sigma 3 and V1, V2, V3, right? You know this.
Okay.
Fine.
Right. Right.
Now you want to compute U4 and U5. What will be these values, right?
Okay. Right.
Now there's no there exists no sigma 4, there exists no sigma 5, right? These values don't exist because it's a diagonal matrix. So
Okay.
5 by 3 diagonal matrix, right? So three columns. So 0, 0, 0 here, right? And 5 rows. So basically 0, 0, and 0. Now everything here will be 0. This kind of matrix you are getting sigma 1, sigma 2, sigma 3, and all other entries are 0. So now you don't have sigma 4 and sigma 5. Then how will you get u4 and u5? You can simply, you have, let's say you have no, each u belongs to R5 space, right? So ui belongs to R5 space, and you have three R5 orthogonal vectors, right?
Oh, right. Yeah.
So you can always figure out the remaining two using Gram-Schmidt.
Okay. Right.
Fine. Fine. So now any other doubts?
One
Fine.
more doubt is little bit, sir. Like
Yeah.
the doubt is what we have applied this approach is for the tall matrix or to any matrix, whether it is void matrix or tall
It's
matrix. We are
for
going to
tall
pick.
matrix, I guess. It's for tall matrix. You can do the same for wide matrix using AA transpose, eigenvalues of AA transpose.
Okay, just opposite. So that will come the opposite of this, no?
Right.
Reverse,
Huh.
like
No, the decomposition will be similar, but again,
same.
uh,
So first
you
we
will
have to do
always
the
be able
transpose.
to write it as U sigma V transpose, but yeah, how to compute that will be different.
Hmm.
So basically, in linear algebra, usually we try to avoid this fat matrices because the system is underdetermined, and uh, this is useful when you will learn about this concept of constraint systems. Then you will know how to solve these kind of systems, but you should know how to compute the eigenvalues this for this kind of system. And eigenvalues of A transpose, the cousin matrix here, right? Fine. So this is it. And then the next concept was like how to use this kind of everything that we saw in this course and their applications. So first thing we saw that how to use something for encoding signals, right? Audio signals. And for that you saw something known as discrete cosine transform, right? How it comes from, where it comes from? It comes from the Fourier basis transformations, right? So what are Fourier basis? Similar to any basis transformation, Fourier basis is essentially useful for transforming inputs from the space input space X to frequency domain space omega, right? So Fourier basis is a way of representing input, essentially periodic input, into this frequency domain information. So you have some spatial information, you transform it into some set of frequencies, right? This is what Fourier transform does. I don't think the details of Fourier transform was given, right? If you want, you can go back and see. But what it essentially says that any signal or any function can be represented as a linear combination of these orthogonal bases. And what are these orthogonal bases? The orthogonal bases are 1, coefficient of 1, sine theta, sine 2 theta up to infinity, cos theta, cos 2 theta up to infinity. Basically, 1 is orthogonal to sine theta in the Fourier domain, which is orthogonal to sine 2 theta up to sine n theta, right? And n can go to infinity, n tends to infinity. Again, you cos theta, cos 2 theta up to cos n theta, n tends to infinity. So using this many infinite number of bases, you can represent exactly any function in the frequency domain, right? So this is the definition, this is how Fourier, this is something that has been just given to you, that this is a Fourier basis. So this is it, right? Is this clear, everyone?
Sir, should I ask one
Yeah,
question?
yeah.
Like, what I'm first of all, my first doubt is like if I'm taking a plane 2 cross 2,
Hmm.
can you draw that plane 2 cross 2?
Yes.
Like, we can now, sir. It is a real plane, no?
Hmm.
Because x and y are the real numbers.
Hmm.
Now, the problem is when we take the Fourier transformation.
Hmm.
So actually, sine series is correspond to, I think, if I'm not wrong, that is for the imaginary parts,
Okay.
and cosine is for the I think real parts, because that's only we real and imaginary part what total overall output what we are going to get Again, it
Hmm.
is the combination of vectors, I think. Same
Hmm.
result. So we
Hmm.
get the result. My
Hmm.
problem is like this is the plane now. What we
Hmm.
have is sheet of paper. There is a plane. There is a x-axis.
Hmm.
Now, so if this is x and y axis, this is the plane, real axis plane.
Hmm.
So what is the concept of the imaginary plane? Now, where should I look for the imaginary numbers? I'm not able to
No, those
understand that.
the real complex. Basically, this is the real plane, right? Now, when you
Yeah.
want to define a imaginary plane, that is completely different from the real plane, right? So, in the imaginary space, all the real numbers are represented on a single line, right?
I'm not like I'm not getting like no like if I'm going to write like suppose if on a plane that number is there like if any wave is like moving like what we get the sine wave or cos wave it means ki it is crossing the xy plane also it is touching the xy plane so it means ki when it touches to the xy plane we take as a number only means ki
So
that
there are
whole plane.
different things, right? One, this is the units are completely different, right? Can you compare 10 seconds with 10 meters?
No, that we
No,
can't.
right? The same thing goes on here. It's a space. So one is your well-known Euclidean space, and then another one is a frequency domain. You can't compare these two quantities directly, right? You need
Okay.
some
So
transformation that helps you to map between these two.
So it means ki like now the Fourier transformation what we are getting,
Hmm.
it means ki just we have to take the two dimension only, one with the real part and other with the imaginary part y-axis. There will be no such three-dimensional or n-dimensional concept for this.
Again, the XYZ 2D, 3D that we have done here, these are all spatial spaces, right? These are just spatial Euclidean spaces. Now, when you
Yes.
transform to frequency domain, this is completely different domain. This is not something directly related to the space that you can see.
Okay.
So, for example, when you draw a wave, right? Let's say this is a wave and this is 2 pi as goes from 0 to 2 pi. Now, this is your usual XY plane, right? Usual space where you see. But when you go to the frequency domain and where on x-axis you represent the frequency, then this plane will be completely represented by one single point. That will be point on this saying a frequency of let's say 1 because one wavelength in one time period, right? So this entire wave is represented using a single point on this line in the frequency domain. So these two
That's
spaces are
why actually,
entirely different.
okay, that's why it means ki when we are comparing with the frequency, we get a circular part, no unit circle we get, no? Because that is the xy plane representation what you have drawn above that
Hmm.
is in the real plane and what we you have just drawn that will be in the complex plane no then.
Yeah, this will be in the frequency space, right? And how to represent that frequency space, you can use the complex plane and whatever.
Okay. So okay, that only I have the little bit doubt ki like now this is the real plane so where because imaginary numbers concept actually really I was not getting the parts actually the
Yeah, right. You can go and see some lectures on what we say. I think real analysis and complex analysis. They will
it's very
explain the
tough beyond,
difference.
beyond
But
just beyond
in
this
short, you are simply comparing these two spaces directly, and you can't do this,
Mm.
right?
What our course was there, na, sir, it was very good. Like, na, we
Hmm.
have got, like, although I don't know whatever the marks, but the concept are very clear. What you people have explained, na,
Hmm.
the things are we are able to understand that actually what is happening. No,
Yeah, right.
so the core concept we are understanding. So far, what we have studied, no, so far whether we have done MSc or whatever,
Hmm.
actually just the target was just even the teachers also means I'm not blaming teachers. The curriculum is such is designed in such a way that anyhow you just go to the next class, whether you understand or whether you don't understand. But what this I'm finding the NPTEL course for
Hmm.
the first time I have taken. And I just
Hmm.
have taken the basic one because my maths is not so strong, but still I'm finding very useful and
Yeah,
very inspiring also.
yeah, that's good. Yeah.
Mhm.
So fine, all the doubts are clear, right?
Yeah, sir.
Fine. So this is 4 year basis that has been given to you. And then now again, now I'm talking about something entirely different. I'm not talking about the Euclidean space. I'm not talking about the basis of the space in the Euclidean space like XYZ axis, right? Now I'm talking about something in the Fourier domain, in the frequency domain, right? In that domain, you have the basis that looks like 1 sine theta to infinity, cos theta up to infinity. And these bases are essentially orthogonal to each other, right? These are orthogonal bases, and you can represent any function as a linear combination of all these bases, as similar to in Euclidean space that we used to see, that we can represent any vector using the linear combination of all the bases. Similarly, you can represent any function in the Fourier domain using linear combination of these bases, right? Now again, a smart technique was invented from here. Is you can always choose a subset of all the bases. So for example, you can choose a subset of R2 space in the R3 domain. You can always choose xy axis, xy plane for representing something, rather than using xyz entire plane, right? And similar to that, if you get this cosine series representation, cosine transformation of a function of a signal, right? And this is essentially useful in encoding audio signals, right? This can be useful in representing signals. Again, of by signal, what I mean, you are essentially encoding the frequency of the signal, right? Now, this has been taught in the lecture, so I hope I don't need to
So,
get into
like
the
like
details
for,
of
here
applications,
for the
right?
cost, for considering the cost function, what sir has explained in the lecture, I think,
Hmm.
we should consider the cost function because it is a even function. And for the even function, we get the amplitude means ki, very clearly we can see the I think parts which we can read it out, or maybe we can separate the different nodes. I think somewhat sir has explained in that part. So that part I was not able to understand ki how segregations will be happen only with the cos one and not with the sine one part, if we consider.
Right. You can go back to the lectures and again say, because I don't want to get into the details of these
Okay, I
applications.
think
This is
it is
the
not in the syllabus also, that that much.
huh.
It is just the introduction part. Ki this year it is applied. I
Yeah.
think that much only is there.
Basically, this
Okay,
is the last session, and I need to finish the problems also,
okay,
right?
okay, okay, okay.
So basically this was taught in the lectures, and then you saw how you transform a function into its Fourier domain using this integral formulation. What you're doing, you are simply doing the dot product with the basis. And in future, you will get to know that this integral is essentially a dot product defined on the basis, on the Fourier basis, right? So this is how also you represent, get the coefficients in the normal basis that we have seen, right? Now, again, using the ideas of this discrete cosine expansion, JPEG was developed for compressing images, right? This has been again taught in the lectures. And the last concept that I'm interested in, the principal component analysis, it just says that, let's say you have a set of data points, right? So can you find its and so no, the good example would be, now let's say I have a mapping, I have some statistical data. So let's say what should I say? Yeah, let's say house pricing information. So let's say a house size, right? Based on the house size and the and let's say condition may be a number between 0 and 1, 0 being the poorest and 1 being the best, and house size be any a natural number, right? So and you choose you have some data of some location. So house 1, the house size was let's say 100 meters squared, and the condition is zero point 0.5, half built. Second house of size 50 meters squared, but completely built, right? And again, let's add a cost to this. So let's say it's in rupees. So rupees, let me use something like this, rupees 100 here, then rupees 200 here, right? Something like this. So can you predict, can you find out what will be the data for this kind of house, right? 120 meters squared and condition is 0.8. What will be the cost? This kind of problems you can use from so you are essentially trying to build up an intuition on what the data looks like, right? So you represent this using a matrix of dimension 2 by 3, and then you define the matrix, cousin matrix M transpose M, which is essentially the covariance matrix, right? Now, how to represent this matrix M? You have to scale and transform all the entries. so that they have the same range. For example, if you have 100 here and zero point 0.5 here, you directly can't find any variance between these two. But if you scale all the entries, these three to 0 to basically in 100 to 120, you can write these as what you can write is as 1 0 zero point 0.2 something, then 0.6, and then 1, something like this. Then everything will be between 0 and 1. Again, similarly here. And from here, you can build the covariance matrix and transpose M, find the eigenvalues from this matrix and the eigenvector, and you will be able to find the principal direction of variation, right? So for this kind of data, right? So this was data, how it was distributed, and you will be able to find a principal direction in which the majority of the data fits in that direction. And using that data, you can do multiple ways, like predicting the house rent in the for a new kind of house in the new condition, right? New house size and new condition. So I hope that I am doing this very fast, and this is very short introduction to PCA, but I just want to give you that this is something that was done. That's it, right? Is this clear, everyone? We will do the problem on this also. So hopefully this will be cleared up. Right?
Sir,
Yeah.
so so the principal components that you wanted to refer, uh,
Hmm.
so you mean this that this sigma 1, sigma 2. So first you said that any matrix capital A using
Hmm.
SVD can be written as a sum of rank 1 matrices.
Yeah, right.
Uh, right. So when you are considering the sigmas in the
Hmm.
descending order, then
Hmm.
if you're taking only the first, let's say first four components,
Hmm.
so first four sigmas. So
Hmm.
are you trying to mean that this first four sigmas, they are referred to principal components, which
No,
plays the
no,
most
sigma.
significant
This
part?
is not. This is yeah. Well, in a way, like when you do M transpose M, you are essentially choosing the first four singular values. Right, right. You are right.
Okay.
All right.
So this principal components, they are a
Hmm.
direction or like they are this matrices itself?
So principal, there are principal directions, right?
Right.
And the
So
scaling along those directions are essentially the principal components. That's it.
okay. So only those directions that mattered the most, and
Yeah,
even
right.
if we
Hmm.
discard all the other components, then it will be not that of a big deal, right?
Yeah, it will not that of a big deal. It can be used for compression tasks. Yeah,
Okay. So,
fine.
sir, how to find those directions particularly? Like, what operation will we perform to find those directions?
Again, what you have to do is you have to build up the normal M matrix that represents this data. For example, for this
Right.
will be 2 cross 3 matrix. Make sure that the all the entries in the matrix, all the columns are normalized. So there is something known as normalizing the entries to have a uniform same what we call variance, same variance and standard deviation, no variance, mean and yeah, same mean
Okay.
and same variance. All the columns should have same mean and same variance. When you have done this kind of normalization, then you will get the final filtered MCAP matrix. Then from the MCAP matrix, you can build up the covariance matrix M transpose M, MCAP transpose MCAP. That essentially tells you how a quantity is varying depending given the other quantities variation, right? And then find the eigenvalue decomposition of this matrix.
Okay. So now the eigenvectors are essentially the principal
Principal
components.
components. Yeah.
Okay. Okay. Okay,
Principal
sir. Yeah.
directions basically.
Okay, sir. Yeah. Thanks.
Fine. So let's finish up the problems really quick. I hope most of the topics are covered, right? Consider the following two statements. Eigen decomposition for every matrix exists, or singular value for every matrix. We already saw that eigenvalue decomposition does not exist for every matrix. It only exists for the diagonalizable matrices. SVD exists for all matrices, right? Statement 1 is false. Statement 2 is true. Option A, right? Everyone, do you have any doubts in this?
No, sir.
No, sir. Yeah.
Right. Next question. Given vector u1 u2 v1 v2 and A is a matrix that is essentially equals to u v transpose, then the non-zero eigenvalue of A is, right? So u1 v1, u1 v2, u2 v1, U2, V2, right? Now what you have to do is you have to find the non-zero eigenvalue of A. Anyone?
Yes, sir. Doing in a minute.
So we all know how to do
So
eigenvalue
one
decomposition.
of
You can
them,
figure it.
right?
Hmm?
It's a singular matrix first of all because rank is
Hmm.
one. So one of the eigenvalues is zero, and the sum of the like the trace should be the other
Yeah, right.
eigenvalue.
Hmm.
But
Hmm.
there is no such option. No? Okay, there is. We transpose you. Right. We transpose you. It would be so U1 V1 plus U2 V2.
Right.
Option B.
So option B is correct. Anyone, do you have any doubts in this?
No.
So basically, this is 2 by 2 matrix, right? And singular. So rank one. So only one non-zero eigenvalue value and sum of eigenvalues is equals to trace of A, which is equals to U1 V1 plus U2 V2, which is equals to U transpose V, right? Okay, done. Nice. Now let's move on to the next question. Which of the following cannot be a characteristic equation associated with a real symmetric matrix? Everyone, do you remember the properties of a real symmetric matrix?
Yes, sir. So option C cannot be because in that case lambda turns out to be an imaginary case.
C. Right.
Yeah, you get real eigenvalues, right? So option C is correct. Great. So let's move on to the next question. A is a 4 by 4 real matrix with some eigenvalues. The eigenvalues are -1, comma 2, comma 3. Will the algebraic multiplicity? Everyone, do you remember this or I need to go back? You
Option B is
remember
6.
this? Everyone?
Yes, sir.
Right. So basically it says -1 repeats 2 times, right? 2 repeats 1 time, comes 1 time, and 3 repeats 1 time, right? Then what is the determinant of A, right? So basically we
6.
all know that determinant of A is equals to lambda 1 into lambda 2 into lambda 3 into lambda 4 into lambda 5, right? Where lambda I belongs to 1, 2, 3, 4, 5 are eigenvalues, right? Right? Now we all know this, right? This is clear. There is no doubt in this, right, everyone?
Yes, sir. Yeah.
Now we all know the algebraic multiplicities, so we can figure this out that lambda 1 will be -1, lambda 2 will be -1 since lambda -1 has multiplicity of 2, lambda 3 will be
2,
2, lambda 4 will be
3.
3, right? Okay, yeah, it's lambda 4 up to 4, right? Yeah, right. Now the question is, what is the determinant of A? Again, you can solve this. Determinant of A is equals to -1 squared into 2 into 3. What is the answer?
Six.
Uh, it is
Six.
-3, right?
Okay.
Acha, it's 3, right? It's 3, right? The
So
question was,
6.
6 will be
Six.
the answer, right? Option B. Anyone, do you have any doubts in this?
No, sir. Clear.
Right. Next question, the eigenvalues of the matrix A transpose are 1, 4, 9. Then the non-zero singular values of A are
1, 2, and 3. So the positive
1, 2,
square root.
3.
yeah.
Option A. 1, 2, 3.
Sigma 1 is equals to square root of lambda 1 squared. Oh, sorry, lambda 1, right? So sigma 2 is essentially square root of lambda 2. Sigma
So
3
1,
is
2, 3.
equals to square 3. So 1, 2, 3, right? Any doubts?
No, sir.
Right. Last question. If the rank of a 7 by 3 real matrix A is 3, then the number of non-zero singular values is anyone?
3. So
Three.
rank is equal to
Three.
3.
Why?
Uh, so basically, it's a property which we can derive from that part. That yeah. So
And number of non-zero singular values is equals to rank, right?
right.
Now, how can you say this very quickly? Let's say if I want to verify this, it's very simple. You are saying that you can write any matrix A as U sigma V transpose, right? Now, let's say A has a rank of R, right? U is a full rank since orthonormal matrix. V transpose is also full rank, orthonormal matrix, right? And A is M cross N, U is M cross M, and V is N cross N. So the rank of A is R, U is M, and rank is M, and rank of V is N, right? And R is less than minimum of less than equals to minimum of M comma N, right? Then this means that there has to be some matrix that is having rank less than M and N, right? So then you have to ensure that rank of sigma has to be less than equals to min of M cross N, which will be equals to R, right? This is how you can verify this also very quickly, right?
Uh,
Everything clear?
Uh,
Yeah.
sir.
so like
So
we can take like
yeah.
this also. If I'm not wrong, like A can be written as sigma
Hmm.
summation of sigma square U V transpose, like
Hmm.
UI VI transpose, and
Yeah.
each one is of rank 1.
Ha ha ha.
And since A is of A rank is 3 or 4, whatever it is given, so each is one rank. So I think it will be 4 rank only. Means because it depends upon the sigma square only, no?
Yeah. Right. So basically, this essentially means basically you if you're adding three rank one matrices, the most rank you
Yes,
can achieve is
yeah,
rank
yeah. It
three
will be sigma
or less
square.
than three, right? Yeah. So is this
Right.
clear?
Sir, but for this instance, where
Huh.
UIs are linearly independent as they are
Hmm.
orthogonal,
Hmm.
right? So for this instance, can we say that the number of linearly, can we, first question, can we say that these matrices are linearly independent? Linearly independent is a word that we use for vectors, but can we use
I
them
mean,
for
linear
matrices as well?
independence of a matrix essentially depends on the column vectors of the matrix. So you can always say that the column vectors of this matrix are linearly independent. You right? You don't say
Okay.
that a matrix is linearly independent. You say that the column vectors of a matrix are linearly independent, or the row vectors of a matrix are linearly independent.
Okay, right, right. So I think, sir, I guess sir was informally using the term. So
Hmm.
in his later notes, he wrote something like linearly independent matrices because of the
Hmm.
same reason which you said. So UI VI transpose, U2 V2
Hmm.
transpose, and U3 V3 transpose. These all
Hmm.
are linearly independent. Let's say
Hmm.
in terms of columns or matrix definition, whatever. So, but
Okay.
in yeah, in that case, can we say the rank will be sum of these ranks? At most, the bound is a property that I know that rank of A plus B is less than equal to rank A plus rank B. But if this matrices they hold such property, as in this case, then can we say equality occurs that rank of A plus B equal to rank A plus rank B?
Um. mm, Okay. Not necessarily, right? For general matrices, let's say if your matrix A has rank, A is an cross n matrix and its rank is n, another matrix B has a rank n and its rank it is n cross n matrix, then A plus B don't have a rank 2n, right?
Right, right. So I'm asking for what kind of matrices the equality holds. Basically, here I can see equality is holding, so that's why I'm asking. Here, rank A is some of this rank one matrices,
I
right?
have not come across such let me see if these matrices exist.
Okay.
Right. So, I mean, this is not always true, and I don't think there's exists some classification, but there is something that exists is writing in our diagonalizable matrix. Let's say you have a diagonalizable matrix M, then you can write it as sorry, yeah, you can write it as P lambda P inverse. Then you can always write this diagonalizable matrix as a sum of n rank 1 matrices.
Okay, right. Yeah.
Basically, I mean, I haven't seen this example like for general matrices, but yeah, this is something that we use very well. That you can always write a diagonalizable matrix as a sum of rank 1 matrices.
Okay, so I was trying to generalize the case, if I can, that when rank of A plus B is equal to rank A plus rank B, for what kind
Hmm.
of matrices A and B?
Hmm.
Okay, that will be a question which I'll write, and later I'll think about this.
Yeah, I don't get the question here, right?
Yes, sir. For the time being, it's fine. So I get this part that for diagonalizable matrices, it is happening. I was trying to generalize it actually. So for what kind
Yeah.
of matrices that happens?
You will have to find some application where you will always get this kind of combination, right? That you can see on the screen.
Right.
So, or something like this. There, if there is some real world application where these kind of matrices happen, then there might be some generalization.
Okay.
Like again, here the rank is equal to sum of two
Yeah.
ranks, right? This is specific cases. Any other doubts, everyone?
No, sir. For this question, it's fine.
Yeah. So that's it for today, right? So I think we are done with the course for this semester. Fine. If you
Thank you,
have
sir.
any doubts, you can ask me or we can end the session.
Yes, sir. I have two doubts basically.
Yeah.
So one is related to SVD, and let me share you in the chat. So I have the
Yeah.
picture of it. One question here. Just one second. Oh, yes, I'm sending the question in a minute.
Given matrices A is singular, B is singular.
Yes, sir. This question. So can
Oh,
you bring it to the page? So yeah.
mm. Yeah, given matrices A arc is 6 cross 3 with singular value 753, B will be singular values 2 to 1. Hmm. Mm. So let me bring the problem here itself and let's see. You have a 6 cross 3 matrix with the singular sign 5 3. B 6 cross 3 2 2 1, and C is equals to A into B. So 6 plus 6, suppose we have first SVD, right? C equals to U sigma B transpose. Right.
Sir, C is that augmented matrix. So first three
Acha.
columns of A and then three columns. Otherwise, multiplication is not possible.
Right. Y. A into B, right?
Right.
B.
Yeah.
How small can this be? Right. So where did you get this question?
So it is basically it's a gate related question, and this original source is some Berkeley or some they used in midterm question.
Oh,
So
nice.
and some people like posted it in a gate question. So the original source is Berkeley. They posted in some midterm time kind of question.
Yeah.
The question is valid. Uh,
Hmm. Okay, fine. So let's try to solve this. Fine. So E can be written as U sigma V transpose, and B can be written as gain. So A looks like this. Some U 753, right? 7 6 cross 3 to 7 5 3, and then 0 0 0 0 0 0 0 0, like something like this. So how can we build this? Hmm. We are the possibility somewhere. What is the smallest single value, right? How small?
right. I was thinking them the easiest example I was forming in my head that putting the singular values in the diagonal entries. So for A matrix, I was thinking exactly what you have wrote. So 753, only that case.
Mm.
U and V would turn out to be some identity matrix of some order. So and similarly B matrix I formed diagonal
Mm.
entries 2 to 1. So this C matrix, it is a diagonal matrix. Diagonal entries are these all the singular values of A and all the singular values of B. So
Mm.
753, 2 to 1. Now I was thinking how small can sigma 1 be? So uh,
The thing is, right, so how to approach this problem is how small sigma 1 can be is essentially saying what is the basically first of all you need to know the properties of this SVD. You will see that sigma 1 will be greater than sigma 2 will be greater than sigma 6, right?
right,
Now,
they are considering that.
huh? What?
Yes, they are considering that. So I forgot to mention one thing. So sigma
Yeah,
1, they are considering the maximum singular value of C
yeah, right.
matrix.
And
Right.
then the question becomes now how to see this problem is what is the what is the bound on, let's say you have this some choose some vector x. So what
Right.
is the maximum
Exactly.
norm of the vector x, right? What is the norm of this vector? So you have to max this with respect to x, right?
Right.
This will
Yeah.
give you the bound on sigma 1. This will be the sigma 1, right?
Mhm. Correct. Yeah.
Right. For this, you need to understand how how essentially matrix induced norms are defined. And I don't think these topics are covered in the lectures, right?
Okay, but can't we think of it from the idea that you are telling me that
Mhm.
uh, see, actually that's why I asked you that question in the first place, that the
Mhm.
maximum singular value it
Mhm.
represents the stretching, maximum
Mhm.
stretching. So
Ah,
yeah, that's what you told. So so tell me one thing. Why are you saying that we need to go to matrix induced norms or something like that? Why can't we find it from the properties of uh, SVD only? Or uh,
okay,
so
fine.
I don't.
So basically what happens is how to argmax this function, right? How to find
Okay,
the
right.
maximum vector in the input space, how to find the maximum vector x in the input space, find the vector x in this input space such that c into x will be maximized, right?
Right.
So this is the problem, right? How to solve this problem? Like, have we seen something that helps us to solve this? That is what I'm questioning,
Okay, okay.
right?
Not directly,
And
but okay.
and again, directly we can't say anything about this matrix, but let's see if we choose some vector like this, right? Such that it gives us ax plus 0b, or if we choose a vector like this, 0y, right? 0a plus by, right? Something like this. Then from here we can say that the maximum singular value would be what will be the singular, what maximum stretching will be the singular largest singular value of a, which is sigma 1 of a. What is sigma 1 of a here? 7,
7.
right? And from here we can see that the maximum stretching we can get is what is this
7.
here? 2, right?
Okay, true. Yeah.
Right?
Yeah, right.
Fine. So from here we can see that 7 is also achievable, right? 7 is the number that is achievable. 7 is the scaling that we can achieve from this kind of matrix, right?
Right. So with the diagonal example that I formed,
Mm,
I got 7 is coming to be an answer. That is, first matrix A is
mm.
diagonally placed 7, 5, 3. Second matrix B diagonally placed 2, 2, 1.
Yeah, right. But you're directly ignoring the entire matrix, right? Just by considering it as a diagonal matrix, right?
Right. This is just a small example of it.
Right. You are just proving it for some specification of this matrix. Given that
Yeah,
matrix
yeah,
A and B
exactly.
are diagonal matrices, can you prove this?
So I was not able to generalize it or how to proceed for a general matrix. So the
Hmm.
thing that you did actually, I have one doubt. So can you scroll down a little bit?
Hmm.
Yeah. Okay. So you basically you okay, what you did here was uh, AX. Okay. So you're considering the partition matrix A
Hmm.
B. Okay, and you are multiplying AX plus 0B.
Hmm.
Okay. Right. So this kind of a vector has. Okay, right. So for this example also, 7 is like the minimum thing. But
Hmm.
can we show that? But for the later example, it is becoming 2, na? The maximum minimum stretching.
Okay, yeah, right. So that you can't directly say, right? So let's say I choose this kind of vector, right? XA, XP. Then it will be written as AXA plus AXP, right? Now this will be C into X, right? X equals to XA, XP. Then what is the singular maximum stretching of X, right? So then
That
from here
X's
you
are
can
of which
figure out,
dimension?
huh?
Uh, Actually, I'm a little bit confused about the dimensions here, whether the multiplications are permeable or not. So XA has dimension.
We are choosing XA and XB such that the multiplication is allowed. So this is 6 by 3. This is 6 by 3. So XA would be 3 by what? 3 by 1, and XB will be 3 by 1, right?
Okay, right. Uh, okay, yeah, yeah, yeah. Okay, right. Mm-hmm.
Right. Then you can write it something like this, right? Norm of this is this.
Oh, nice. Yeah.
Yeah, right. Now
And then can we put some bound?
we might need to use some sort of triangle inequality here.
Right, right.
So this will be less than equals to AXA,
So that would be
AXB,
BXB, na? It
BXB,
will be
right?
BX.
BXB, right?
Norm of CX is this, right?
We all know how small
Okay.
sigma 1 can be, right?
Sir, how we
Now,
place the plus sign first? Like CX is equal to AXA plus BXB. Uh,
right. So AXA, hi, any doubt here? Any doubt
yeah,
till this line?
it will be BXB, right? CX
This will be
equal to.
BXB, right? Let me
Okay,
correct this.
in the next line, in the immediate following line,
So
above it
from
also
here,
BXB.
yeah, hmm, you know that AXA is less than equals to 7, right?
Yeah, right? Yeah,
Again, BXB less than equals to 2.
yeah, true.
Now, can we use this inequality here? So this quantity is less than equals to 7. This quantity is less than equals to 2, right?
Right? Yeah.
Right?
No, I'm saying that we
Hmm.
made a small mistake in the previous thing, no? That is
Hmm.
CX equal to AXA plus BXB. So
Acha,
can you
हाँ,
just correct that
हाँ,
to BXB?
हाँ.
Then we are taking
No,
norm. So norm would be on the whole thing, no? Then we'll use triangle inequality. So norm of AXA plus BXB. We took the norms individually.
oh,
I think
right,
we
right,
made a
right. You're
mistake
right.
there.
You're right. You're right. Yeah. Let me rewrite this. So this is equals to norm of AXA plus BXB, which is perfectly fine.
Right,
And then you can put a limit on this.
right. So that should give us the maximum stretching factor could be 9. So it
Uh,
gives us the upper bound.
right.
Right.
So this
So
is less than equals
that
to
was 9.
7. This is less than equals to 2, right?
Right, right. So at least we know the upper bound now. Now we need to find the lower bound. The question actually asks what is the minimum sigma 1 that can be.
Yeah. So the thing is, the minimum stretching you can get is at least 7 or 2, right?
Right.
Okay. Acha, so we have achieved the upper bound, right?
Sir, I think Satinder is muted and he wants to tell something. So
Okay.
he sent a chat or something. Can you unmute him?
So Jordan canonical form. So okay.
Uh, I think he cannot unmute himself. Uh,
Right. So but yeah, these concepts are not completely related to this course, right? I'm not sure it will be helpful for others or not.
okay, okay.
Let me allow the mic. Yeah. Right. Yes, Satinder, what do you want to say?
Just I was saying ki, what the question may be, it may be done like Jordan canonical form is also there, no? That is relative to this only uh, singular values like sigma. So
How
we
will
see
we
the number
proceed
of
using
block.
that?
I don't have the clear idea, but still, I think if we make a matrix with that, and then we see ki, what is the repetition of that for the particular singular value. With that, we can come to know something. That concept is there relatively. I think I thought ki that can be applied. That I was telling.
Okay, let's not go
Like
to Jordan canonical form. I also don't know that. It might be solved based on that. But I was thinking solely based on the idea of stretching and moving from one space to another. So when we are augmenting, all all the pictures are clear to me. But except this one, that when we are augmenting two matrix, uh, what is happening? Like what does it represent? Because singular values tells me the stretching factors and all. So if I can know that what is augmenting two matrices mean geometrically, then I can connect these dots, I think. So can we try to figure out what augmenting two matrices, which we did here? So C equal to A augmented B, what this means geometrically?
I'm not sure what we can figure anything up from here geometrically because you are simply concatenating the columns of a matrix
Right.
here. So yeah, right. I don't think I don't get what we can. I cannot say directly what we can figure out geometrically from here, right?
Okay. Okay, sir, maybe let's not spend much time here if it is not
Mm.
helpful to others. But if you get any idea related to this, then can you let me know
Yeah,
later?
I will send you. I will send you a solution. So I will basically add the solution in the same sheet as where I upload the videos, right?
Okay, sir. Yeah, that would be very helpful. And sir,
I mean, the
one,
direction is
yeah,
this only, but I just want to like formalize this. Like, how will this be a minimum norm, right?
right.
What is
So,
the
sir,
minimum stretching it can achieve?
sorry, go on.
That's the question, right?
Hello.
Hmm.
Uh, sir, your screen froze, I think. Maybe it's my network issue or something. Satinder, can you hear me? Or can you see, sir?
I am I
Hello.
audible?
Yes.
Yeah,
Okay.
yes, sir. Yeah. I think I had some problem with my internet. So, sir, when we are concatenating two matrices, just for one sec. So basically,
Hmm.
we are adding columns, right? So we are not going to a new space. Suppose A was 6 by 3, and now we added
Hmm.
three more columns of
Hmm.
R6. So we
Hmm.
are remaining in R6 only. The columns are from R6 only. So we just added some more column
Vectors in the
vectors to
R6
it.
space, right? Hmm.
Right.
Hmm.
Uh, so can we try to understand what will happen to C into a vector X and compare to A into a vector Y or B into a vector Y?
Right. We can try to see it like that. Like, let's say xai plus summation x bi, right? But it totally depends on the matrices A and column vectors of A and B, right? Let's say if both the column vectors are orthogonal, right? Orthogonal in sense that A is spanning this space, which is perpendicular to this space, right? I mean,
Right,
sorry. Uh, Orthogonal in sense that any vector in, so this is, let's say, R6 space. So
right,
so A is this, and then B is this, and the only intersection is the null space, right?
right, yeah.
Null, no, sorry, zero. Intersection is
Zero, yeah.
zero, right? Zero, sorry. Intersection is zero, right? Now, if this is one possibility, right?
Mm.
Or it can be something like this because you don't know what is happening, right? Or in fact, they might
Right.
be forming some sort of set that is not spanning the entire R6 space, right?
Okay, right. That might also happen. Okay, sir. You actually give me a hint with that upper bound. So I will also try to think of it from whatever knowledge I have. And
Hmm.
later, if you have some new idea, then let me know.
Yeah, right, right.
And so one more doubt. This doubt
Hmm.
is related to the previous class actually, and we said
Hmm.
we'll discuss it in the next class.
Hmm.
So I formed a question out of it. Let me send you here the question.
Hmm.
Actually, you gave the idea to come up with a contradiction kind of a thing.
Yeah,
Uh,
yeah, yeah, right.
Send you the question here. So yeah, yes, sir. I sent it to the chat. Can you see
Hmm.
that?
Let me see. Right. So let A be a 10 by 10 matrix. Eigenvalues are 5 and 7, lambda 1, lambda 2. AM, lambda 1 occurs 4 times, AM is 4, right? AM is 6 here. Of 5 is geometric multiplicity is 5, and the GM of 7 is also 5. So that these, suppose this is the, acha, again, this is a same question, right? That I raised.
Right. Yeah.
Can we bring up a contradiction from here, right?
Right.
So you have 5, right? 5 and 7. This repeats 4 times. This repeats 6 times, right? So essentially, 5 is spanning the space. The eigenvectors of 5 is spanning 5 by 5 space, right?
Right.
And the eigenvectors of 7 are also spanning a 5 comma 5 space, 5 cross 5 space, right?
Right. So no contradiction can occur on the right hand side. That is a good case. So algebraic multiplicity 6, which is greater than equal to geometric multiplicity 5. So I'm
Hmm.
trying to have a contradiction on the left hand side where AM is less than GM.
Oh, um, hmm. So, okay, nothing is said about the thing, right? Okay. So can we think this A minus lambda I null space of this thing, right? So A minus 5I, how the null space of this thing looks like, right?
Yeah. Sir, I'm coming just back in a minute. Just a minute.
So excuse me, like
Yeah,
hello.
yeah.
So what I'm able to understand, like Rohan may be asking ki why arithmetic mean is always greater than
Right, right.
equal to geometric mean.
Yeah.
Actually, the thing is ki whatever the rank we have defined,
Hmm.
like maximum possibility rank is 4 only for the arithmetic mean, and the geometric mean specifies the null space of that. No,
Right.
if I'm not wrong. So
Hmm.
if the maximum allotted space is 4, so the geometric mean can't exceed the 4 places. Means ki because you have only the 4 seats available. So how on the 4 seat 5% can sit? This somewhat in that scenario. Are you are you getting my thing? Like what I'm saying?
I mean, this is the definition of geometric. This is the
Miss,
definition, right? But let's
like
say I'm saying that eigenvalue 5 is repeating 4 times,
like
and then I'm
so
saying
that only
what is.
actually I was also I was also searching ki what is the problem now with this. So the main actually the next step of the SVD is to convert this matrices what we have got the singular values of m cross n dimension or whatever it is, maybe
Hmm,
10 cross 10 or 100 cross 100, whatever we get. Now the
hmm,
main target is with the singular values we
hmm.
decompose into the Jordan canonical form. So it
Okay.
states that the number of that eigenvalues will be formed. That
Hmm,
is 4. So with that, what the space we get, no? Because
hmm,
corresponding to the lambda, we means in how many blocks we can define. So
hmm.
the to get the blocks, wherever the eigenvalues are there, above to that, but the next will be 1. So that is the Jordan canonical form, and that defines the geometrical multiplicity. So if you are going to break down into that form, so you can't never means all the values will be not in the form of like just what we get, that is space, that no, that is arithmetic multiplicity will get 4 only. It just you can have a look on the Jordan conical form with this proof, because this I have gone through, and this what I am able to understand ki number of blocks what we will be formed that cannot be more than 4 now. That's why it cannot exceed, it can be equal to that, because it is the, I think the what the null space it will be formed, no, for the this one geometrical part, no,
Hmm.
eigenspace will be formed that cannot be more than 4 by Jordan canonical form. It is very much clear that it can't exceed. They have given the examples also. I've gone through it, but
Yeah, right. You're right. That is one thing you can do. Yeah.
actually it is not on a syllabus, no. So that's why
No.
we can't understand. But actually that is a good format, because I have seen in the GRF syllabus also, that is Jordan conical form is there in the GRF syllabus also. So
Mhm.
actually I've not gone in the detail, but or the next step is, no, actually it is the basics only, no. So the next step is to convert this the singular values into the Jordan canonical form. So the very much clear picture we get from there,
Yeah,
because
right. You're right.
there.
So I
Sir,
think you
I'm
guys
back.
can look
Yeah.
into this, right? After the course, right?
Mhm. Rohan, are you
Yeah.
listening? Hello, excuse me.
Yeah, I just came
I'm
back. So
I'm
yeah.
saying the why arithmetic mean is not greater than geometric mean. Just have a look
Arithmetic
on the
mean where?
Jordan
Multiplicity. It's a
arithmetic
multiplicity, right?
multiplicity.
Algebraic multiplicity.
AM
Okay, okay.
geometric multiplicity. Why the inequation holds? It has been explained in that way, ki, like that to your understanding also, but you want the full proof of that. So I think very much it has been explained in the Jordan canonical form. Just read
Okay,
it.
okay.
I'm confident that you will be able to understand that part, because it has been explained that if there are four eigenvalues, so
Right.
fifth cannot exist. Means ki it cannot geometrical mean cannot exceed four. Very well it has been explained. I'll send you the link where it has been
Okay, okay, sure,
explained.
sure.
I think you'll be able
Okay,
to
you
understand that
send
part.
it to me. I'll give it a read, sure.
Okay, okay.
But without using like Jordan canonical form, can we say something related to rank or nullity of it? Like, or is it very much necessary to include Jordan canonical form?
I mean,
No, like
yeah.
what it has, the definition itself says. I've also gone through it. It says ki,
Okay,
like if we have the because very much reason I don't have, but still what it says ki, if you have four eigenvalues, it
right.
means ki only you have the four seats, and the what the geometrical geometric multiplicity is there, that corresponds to the null space. Hello, Rohan.
Geometrical multiplicity definitely corresponds to the null space, right? That part. So A
Uh,
minus lambda
so
I, the null space is the dimension of the null space is geometric
uh, uh,
multiplicity. I'm okay with that.
that, so whatever the eigenvalues we are getting four, so with that means what it can't exceed this one geometrical, that only it was in explained, like you have four seats, so 5% can't sit on the four seats, something like that it has been explained.
But why it can't exceed? That part is also
So,
there. Like,
that one, so what is the next step of this? That one I was saying. The next step, just now, so far, what in our course we are doing for the singular values, we are calculating
right.
the singular values. No? Now the next step is to, after getting the singular values, what is the clear picture of the matrix, that will get by the Jordan canonical form only, because all
Okay,
the
okay.
whatever the eigenvalues we are getting corresponding to that A cross A matrix, whatever means M cross M or M cross N, whatever. So all the eigenvalues we have to plot in that. So Jordan canonical form says ki if there is a multiplicity, like if lambda is has the multiplicity tool or whatever.
Right,
So
right.
the next for the first row, the next column like A11, A12 will be again one. Means ki on the diagonal one, na, if the lambda is repeating diagonally, so above to that one will be placed. Now we have to see in that one ki how many geometrical multiplicity states that ki how many we have the blocks, like how many square blocks will be there in that. So it can't exceed 4. Like if it is 10 cross 10, so number of square blocks within the canonical form cannot exceed 4 with
Okay.
one. Like
Satinder,
if the
let me give it a read,
okay,
and
okay.
if I get any doubt, I'll ping you. I already have your number. So is it fine?
Okay.
Yeah, yeah, cool. Thanks.
Okay, guys. Then let's end the session then. Thanks.
Okay, sir. And so thank you, sir. So I think this is the last session, and we won't be meeting any time after that. But if I still have some doubt,